Assalamualaikum and good morning. My name is Abdul Hadi Mahmud, a PhD student from UiTM Tapa, and my project involved developing nanoporous anodic alumina millirod into an electrochemical immunosensor to detect porcine serum albumin in raw meat. Nanoporous alumina for sensor has been researched as a platform, but exclusively only in membrane form. So, we decided to use nanoporous alumina in its wire form for better handling and easy fabrication without compromising its efficiency in sensing. So today, the title of my presentation is a novel nanoporous alumina millirod immunosensor with gold nanoparticle conjugated with antibody targeting porcine serum albumin. Introduction. I'm going to talk a bit about the background of my project. The reason that inspires this project was the meat adulteration problems that are faced by consumers globally. Adulteration means that a food product fails to meet legal standards. One form of adulteration is adding another substance into a food item to increase the quantity of the food. Meat adulteration is a significant problem as it affects all of us either in health or religiously, and the first way to counter this is by detecting meat adulteration. Identification of the origin of species in meat samples can be made using physical method, DNA-based technique, and spectrophotometry method. Methods to identify meat type are in need to develop faster, cheaper, and safer. Immunoassay techniques are gaining interest due to being low cost and easily applied. Objectives: to fabricate a nanoporous alumina millirod as an immunosensing surface. To develop an immunosensor based on gold nanoparticle and nanoporous alumina for electrochemical detection of porcine serum albumin. To evaluate the nanoporous alumina immunosensor performance in terms of both sensitivity and specificity. Significance of study. The result from this study will give a sensitive, user-friendly immunosensor that is suitable for halal kit detection. It will also provide a more effortless and efficient halal kit for use in detection of meat adulteration. And lastly, this will propose a new material for immunosensor detection. Methodology. Here is the conceptual framework. A general flow for my methodology. First, the fabrication of nanoporous alumina millirod and the functionalization of the nanoporous alumina surface to accommodate the antibody conjugation. And then we perform the bioconjugation of antibody to the nanoporous alumina. Next will be the sensitization of gold nanoparticles and then followed by antibody bioconjugation onto the gold nanoparticles. After that, we start with the development of nanoporous alumina-based electrochemical immunosensing of porcine serum albumin with antibody conjugated gold nanoparticles. Lastly, we finishes with the evaluation of the immunosensor from the extracted porcine serum albumin for detection in raw meats and meat mixtures. Firstly, we fabricate our own platform that is nanoporous alumina millirod from aluminium wire. The nanoporous alumina millirod was fabricated by utilizing double anodization method under these conditions. The next step was the functionalization of nanoporous alumina millirod for the conjugation of capturing antibody onto the surface. Nanoporous alumina was first boiled with hydrogen peroxide to introduce hydroxyl group onto the nanoporous alumina surface. And then it was treated with salinization with aptase, and the last modification was with cultural aldehyde before immobilizing antibody into the nanoporous alumina surface. Good anti-peak albumin antibody was conjugated onto the nanoporous alumina millirod. For the gold synthesization, we opted to go with the well-established Tokavish method, and we continue with the bioconjugation of the antibody onto the gold nanoparticles. The bioconjugation of antibody will rely on the ionic bond between the antibody and the gold nanoparticles. For the evaluation of a nanoporous alumina millirod-based immunosensor, the nanoporous alumina immunosensor was exposed to sample of PSA extract. The sample of PSA was varied in concentration ranging from 0.05 nanograms to 1000 nanograms and was allowed to react with gold nanoparticle stacked antibody before being analyzed using differential pulse anodic stripping voltammetry. The current produced from the variation of sample was observed and recorded. Result and discussions. Here is the scanning electron image for nanoporous alumina millirod. The first two images was taken at 50,000 and 150,000 magnification to show the pore structure on nanoporous alumina millirod after the anodization. The average pore size for the nanoporous alumina was around 166.12 nanometer. Then we take a look at the cross-section of the nanoporous millirod. The alumina layer thickness was measured to be 42.95 micrometer. Then the comparison image of the bare nanoporous alumina without any alteration, and the other was the image of nanoporous alumina after surface modification and conjugation antibody with the captured PSA. The image shows how the interaction of nanoporous alumina surface and target PSA has occupied the surface of nanoporous alumina. The surface modification done on nanoporous alumina has been confirmed by the FTIR analysis. The result in the FTIR spectra show the key functional group that plays important role in bioconjugation of antibody. The hydroxyl group after the hydroxylation with hydrogen peroxide, the amine group after salinization with aptase, and the aldehyde and amide group peaks that come with the cross-link of butyl aldehyde. Sensitivity is an important part of an immunosensor. The more sensitive, the better the immunosensor. For this, the assay platform analytical performance has been challenged using a panel of purified serum albumin from 0.05 nanogram mil to 1000 nanogram mil. Under optimal conditions, purified PSA was calibrated with the detection limit of 0.789 nanogram per mil and a dynamic range of 0.1 to 100 nanogram per mil with an R-square of 0.9935. The repeatability test run for alumina was carried on 1 nanogram per mil porcine serum albumin with a repeat of 5 times, and the relative standard deviation value was 6.58%. This is a good result indicating that the consistent signal was given by our nanoporous alumina immunosensor. Here is the comparison of other developed immunosensor with our nanoporous alumina millirod-based electrochemical immunosensor for detection of porcine serum albumin. As you can see, our developed immunosensor has a LOD on par with the other developed immunosensor. Selectivity of the immunosensor was studied with different meats. Selectivity evaluation with beef, chicken, lamb, and pork was done, and the results have shown excellent selectivity with exclusive porcine serum albumin detection signal only from pork meat samples. The developed immunosensor real applicability in detecting pork adulteration in raw meat have been evaluated by mixing different amount of pork in beef samples. Pork beef mixtures were 0%, 0.1%, 1%, 5%, 10%, and 100%. Excellent specificity with porcine serum albumin, good detection in samples with detection as little as 0.1% pork in meat mixtures was recorded. Here is the comparison of other developed immunosensor with our nanoporous alumina millirod-based electrochemical immunosensor for pork adulterant in raw meat. The developed nanoporous alumina immunosensor has a limit detection on par with the other developed immunosensor. Conclusion. The developed nanoporous alumina immunosensor have a low limit detection of 0.789 nanogram per mil and a good repeatability and selectivity. The real application of raw meat adulteration was able to detect as low as 0.1% adulterant pork in beef. This result indicate that the developed immunosensing platform based on nanoporous alumina millirod and gold nanoparticle has demonstrated a high level capacity to detect pork adulteration in raw meat. It is anticipated for widespread application in food safety and quality inspection. Here is some of the reference in this work. That's all for me. Thank you.